let's jump into it. So we're 30 minutes in, so we're just going to kind of work through this, but this stuff is going to be pretty easy to kind of talk about. So this course kind of started off as a bit of a general kind of, hey, let's look at design. And so we started off when we talked about design principles. You have the concept of LOD, law of diameter. You want to keep your friends close. You don't want to like reach within an object and kind of keep accessing all the kind of inner members of that object and kind of tear them apart and kind of muck around with them too much. And then you have the other concept, which is things such as, I don't know, what's another one? I can't remember the other one I was thinking of before. Um, LSP, that's the one I was thinking of. LSP, which is all about like, I guess LSP and like preconditions and stuff like that, right? So your pre, your post, and your invariants as well. Invariants. And then this is the idea that like you want to kind of keep these conditions that you in place upon your classes so that you can kind of treat the subclasses the same as the parent classes, right? And then, we briefly talk about composition versus inheritance, and we talk about like why do we prefer composition over inheritance? When is inheritance good? And we kind of touch on them, but not really in a lot of depth, honestly. And then we kind of jump into design patterns. And so the big thing about software design is that everything comes down to really, I love this thing moving around. Everything comes down to really one thing. And that one thing is when you're designing software and when you're trying to design software that scales, that's easy to write, that's easy to maintain and everything, the simplest solution is basically the solution that we go for. And typically, this is kind of like Occam's razor, I guess, right? And so OOP and all that kind of stuff is meant to make stuff simpler. And so what can happen, right? And this happens to interns all the time, or really anyone who's just learned OOP, really, is they kind of grab these concepts of OOP and they kind of fall in love with the concept of it. And so then they start seeing, they become like a hammer, and so they start seeing nails everywhere, and they start seeing patterns everywhere in real life, right? And they start applying patterns to every inch of the code base, and then they get a code base that's like 10,000 lines long, and it prints "Hello World," right? Because what they've done is they've kind of over abstracted everything. Oh, what if we don't want to print hello today? What if we want to print goodbye? What if we don't want to print the world and we want to print the person's name? And so they start worrying about all these kind of like edge cases of like, what if this? What if this? What if this? That they don't kind of break it down to what am I actually trying to build? Like, what am I actually going to use? What's the common use case that my clients are going to need? And this is pretty much the kind of one fix against over abstraction or over engineering, is kind of aim to write it as simple as possible. And then once you've written it simply, think about the consequences of that simple implementation. And you want to try to wrap the solution or try to maybe change the solution or, maybe implement a pattern or whatever to kind of make that solution more robust, right? And easier to refactor over time. But you don't want to make it so it's more flexible. If anything, you want to make it honestly like less flexible, right? The whole point of software is not to make an extremely flexible design, because as soon as you have flexibility in your system, someone's going to break it. As soon as you have a button that can be pressed, someone's going to press it in a way that you didn't expect it to be pressed. And so you want to restrict your design so that you can know exactly what the edge cases are, so you can test exactly those edge cases. Because otherwise, sure, your design's really general, but you haven't tested 80% of your edge cases, which means your design isn't general because those 80% of those edge cases don't actually work. And this is kind of really what software as a scale is kind of down to being, is that software as a scale comes down to two things. The first thing is like the development of the software. Development. And then the second thing is the maintenance versus the deployment processes versus the actual like performance of the code. And what happens is people often kind of focus very heavily here, right? They focus very heavily on writing the initial feature, but they forget all about this. And so this is not really the problem. You know, we have Git, we have Agile, and most companies don't actually use Agile. They use like this kind of bastardized version of Agile that kind of works for them. So they're like, oh, I love this part of Agile. I love this part of this. I love this part of this. And they kind of break it apart and have their own way of doing things. It's kind of very rare to see a place that uses exactly what Agile is. Just because it's so dependent upon culture and so many things, right? And so this is kind of like a solved problem. This isn't really hard. Like, it's got its difficulties, but it really isn't that hard to manage all that stuff for 5 people versus 50 people versus 100 developers. Once you have, you know, scrum masters and project managers and you have like somewhat competent people who are like able to work with other people, and you go, okay, hey, we have a product change that's going to change this module A, and then someone goes, oh, but I got to do a product change to module A, and you guess what you do? You either have it so that they work together, or you have it so that one person's change goes out first, then the other person works on the other change. Because at the end of the day, most likely the changes have pretty flexible deadlines, so it's not like they have to be done at the same time. If they have to be done at the same time, then they just have to work together. Or it's done by the same person, typically. You know, it depends. And so this kind of side of like managing all that is hard, but it's 100% doable and it's pretty much solved. And so the big problem about scale comes down to this. Like, this is the problem. And the reason why is this. Let's say you manually deploy to a client. You know, for example, you're setting up a portal for a client to use. Let me show you an example. So this is an example for my work. It's just some random portal. I can load it up. I don't know if this has enough resources to run, and this is probably not a good time to run it because everyone will be testing it, but we will see if it will be fine and happy with us. I don't think it has all our data, so it should be fine. And so if we have this, and this like contains like a bunch of analytics, there's a bunch of stuff to this. And yeah, that's funny. I guess that visual is like probably just hard coded. Is it? Oh my god, that's just an image. That's really funny. This is a demo portal. So there's like some of the stats are just like literally just images, and this is literally just an image that's hard coded, which is really funny. Anyway, like that's a really good technique, by the way, in demos. If you want to do demos for people, you have certain visuals that are hard to create. You just like literally do like hard coded images, and it works really well. Anywho. And so you have like all these portals and stuff, and you know, these are unique for each client and so on. You know, this is a demo one. And you know, this allows you to like view data, and you know, this is going to be completely uncached. It's going to be a bit slow because we don't make this stuff fast because it doesn't need to necessarily be that fast. But you know, you could have like various things. You could like, I don't know, I guess like say, okay, tell me the gender and tell me the driver score per gender or something like that, or I don't know, show me like the cards, right? And so you kind of get all these like ability to do this. That's kind of a weird one to do it by. It's grouped by region. And so you can see everyone in Greater Sydney or everyone with certain themes. I guess we don't. Oh, we do have themes. Look at that. We got staff members, good ranges, and we can like zoom in and look at these cards and stuff like that. And so this stuff is pretty cool. And we create these uniquely per each client. But the problem is that this is a unique instance. Which means if we want to make a change to product and we want to upgrade every client, if we have 100 clients, that's 100 unique deployments. That's hell on earth. Like, that's impossible to scale. Because each one requires testing the change, testing the upgrade, testing the PVT, making sure the deployment went well, actually having someone deploy it, doing all this. That doesn't scale. You can't do manual deployments. And so pretty much my job for the last 3 months has been converting us from manual deployments to automatic deployments. I've been doing much other things, but that's kind of my main thing. And so now we have this automatic process where we can just like push a change and it will like stage it to certain clients, like low risk ones and high risk ones and like, you know, very, very high risk ones. And so what you do is you have this like slow change over time. And so what that means is even though each client has completely unique configuration, this one has a basket size, a different client could be a childcare, so that makes no sense for childcare. And they've got different ones, they've got unique visuals and unique changes, all this kind of stuff, right? And there's probably about 4,000 or 5,000 lines of config per one, minimum. And I'll show you an example today because I think this stuff is useful, like showing a real example of design. And the problem comes down to how do you handle deployment at scale? How do you handle this kind of stuff? And the answer really is way out of scope of this course, but is kind of really comes down to the design principles that we've been talking so far. And it's this kind of funny analogy of it that I think it can kind of be appreciated in some ways. And so, for example, when you're looking at it, you're going, okay, I have a bunch of unique tenants, right? And a tenant is just a name for like a client. So for example, let's say UNSW is one of our tenants. They are not, but let's just say, for example, let's say we have a bank as a tenant. I don't know, the Bank of Braden can be good enough. Bank of Braden, BOB, Bob. And then we have like maybe another tenant, which is like, I don't know, UCID, sure. And so these are like our three clients that we're accessing. You said boo or whatever. We can give them low ratings, why not? And so if we have these three clients and we want to deploy to these clients and we want to manage these unique instances, how do we do that? What's a design principle here that we can do, right? And so suddenly now we are actually applying design principles not just to code, but to our entire process, to how we build things, to how we schedule things, to how the actual resources themselves are allocated. So now suddenly each one requires a unique app service, which is a special, basically just like an app in the cloud, right? It's just like a website in the cloud. But also each one now also needs a completely unique server SQL DB. So this is their database. This stores all their unique data. Why do they need a unique one? Well, because of safety reasons, right? We don't want to have, risks of clients being on the same database, especially for banks. That's a really big deal. Banks have their completely unique environment. So banks are nowhere near anything else. They're completely segregated because they have all these strict financial requirements. And so what you end up with is this kind of containerization here. And so you kind of develop these kind of unique patterns here. SQL is that Java too. Oh, do people not know what SQL is? I presume people do not know what SQL is. SQL is a way to query databases like this. So you can like say select everything from this table, and table is like kind of like big Excel sheets kind of. Oh, did I? I don't know. I just presumed that people don't know what SQL is if they don't know Java too. I think I probably did. I don't know. I'm bad at getting jokes via text apparently. Interesting. Anyway, and we have some really crazy SQL stuff, and it turns out that when you're writing SQL queries, the same design principles that you make in code applies to your database model. So when you're storing your database model, you have users that you're storing inside a database because you want it to be persistent, and then you have like logins, or you have, for example, the physical data itself, which we typically call like a leaf level. And I don't really want to get into like how data is represented, but it's something called OLAP. Typically, it's kind of like a generic structure. And the idea of it is that you represent it as like some kind of hypercube. You can like look it up and kind of understand how that works if you want. And so you kind of have all these various different tables, and they have relationships between them. And those relationships have cardinality. Those relationships have quantification about one or many, which is the cardinality, but they also have like, is this a coalesce relationship? Am I going to delete the child when I remove the parent? Which is, guess what? Composition. Are they independent? And so suddenly these like concepts that you experience, you're going to see constantly. Because guess what? They're not coding concepts. They're just generalized design concepts. And design principles really aren't just patterns. They're not just, you don't just like go, oh, I want to design a strategy pattern. You just like end up writing it as a consequence of needing that level of separation. And so, for example, here, when you go, okay, hey, this client needs Azure SQL DB, right? Which is like a cloud service. But UNSW, or they've got their own SQL database they want to use because they're kind of rude and nasty for whatever reason. I don't know why I'm digging on UNSW. They've got their, I mean, they actually technically use AWS. So they want to use AWS, right? And so they want to use an AWS SQL DB. Functionally, it's still SQL, and it's probably still the exact same like type of database. It's probably still going to be a Microsoft SQL database, but maybe it's not. Maybe it's literally something called Postgres, which is a completely different dialect, a completely different language. And so you need to abstract the way you store your data based on the type of provider, which is just a strategy pattern. You're strategizing how you're storing your data. And then you go, okay, hey, I'm going to deploy to these clients. And so what I need to do is I need to figure out which client is in which bucket. Okay, so first thing, let's say this client is low risk. So is this client. So we're just going to upgrade them every single time. We're just going to basically broadcast directly to those clients every single time. But this one's high risk. And so when we want to upgrade these databases, right? Well, not these databases, but these clients. Maybe they're running on a virtual machine, right? And then this virtual machine could be a polling virtual machine where it constantly asks our deployment server, hey, do you have an update for me? Do you have an update for me? Or it could be a observer polling machine where it observes updates, and basically the system will push and go, hey, I want you to update. This pushes, hey, I want you to update. Hey, I want you to update. I go and make a change to production. I push that change to a master branch. That then goes and kicks off a unique build for my change. That build then goes onto a unique app called development or something like that. What is that? That's an observer pattern. You're observing a change. I can show you a real example of that. So one of the applications is something called SurveyX. Oh, look at that red. And this SurveyX application automatically gets triggered every time master gets changed. And it pushes not only to Octopus so that we can do deployments to clients. So this is actually a single application, but we have like EU instances and America instances and Australia instances and stuff like that. But it also pushes to a unique app service so that testers can test it. So every time I push to master, I get this build. I'm observing these changes. I didn't sit down and go, I want to write an observer pattern here so that I can observe every time I push to master. I go, well, okay, I push to master. I want to have a process that automatically builds. Okay, then I need some way to observe these changes. Okay, I'm going to set up a trigger that will observe these changes. And this happens every time we do things. You know, a good example would be business rules. So I have a series of rules, and these rules are very important. So for example, let's say I have let's say we are, McDonald's, which isn't actually one of our clients, so I can talk about them. So McDonald's, right? They go, hey, we want to have a program where we're going to send out some kind of relationship program to say, hey, you've just recently bought a Big Mac at one of our branches. How did you find the Big Mac? You know, rate this Big Mac. Did you like it? Did you hate it? Whatever, right? Or you bought nuggets or chips or whatever. And so you have this kind of relationship program here. And so what you do is you go, okay, they give me an Excel document, right? And this Excel document contains the list of every person that bought a Big Mac in the last 2 days, because maybe we run this every 2 days. Then we're going to put this into a system. It's going to load itself into a table. It's then going to pull those records from the table and get them ready to send. But to get them ready to send, it needs to check some conditions. Okay, what conditions does it need to check? Well, it needs to check they have a valid email address or an SMS address. Maybe we want to send them SMS if they don't have email. Or maybe we also want to check another thing. We want to check that they actually bought the Big Mac in the last 30 days. These are business conditions that are set by the company we work with. And so we need some way to abstract these. And I mean, can someone tell me what this kind of pattern is? You got it, right? And so what you find is you go, oh, I need to write a composite pattern for this. But you don't really sit down and go, oh, I need a composite pattern for this. You sit down and go, okay, well, I need some way that I can have it so I can have this nesting of conditions where I have like some kind of abstract syntax tree, right? And like this is technically how we store them, but you could have it as like a string that's interpreted. Jeez Louise. And you end up with the kind of impact of, oh, hey, in the end, we end up with a composite pattern. And you see this with a lot of things. And so there's one kind of analogy I quite like. And it's this kind of, there's a few, actually. Let's first talk about some of these things. So the first thing is like how you actually build a system itself. And so I think we don't really talk about this, but there's this concept in the industry of monolith versus distributed / microservices, right? Technically, there's a distinction between these two, but let's not be too gatekeepy about it, right? Like I'm trying to speak at like some high level, so some of the stuff I'm going to say is going to be overly trivialized. And if you know a lot about this, you're like, oh, that's not entirely correct, blah, 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 according to XYZ, it's fine. Like it's meant to be a general introduction to these concepts so you can kind of understand them without needing to talk about like 6 hours about what a monolithic application is. And so the kind of breakdown of what these things are is the monolith is like all the code is in one big code base. Distributed versus microservices is that you have like a bunch of mini services that kind of abstract just one part of the system. And so, for example, you may have a microservice that does sending an email. But actually, what you would do is you would have a microservice that probably sends an email via X provider, another one via Y provider, and another one via Z provider, and it just doesn't really work that well. And so it's kind of a degree. That's the thing about microservices and monolith, is it's not like a binary thing. It's not one or the other. It's a degree of how far you go. So you may be like, that's crazy, and it kind of is. So, okay, I'm going to send an email via any provider. So what I'm going to do is I'm not going to have 100 microservices just so I can send to 100 different providers. I'll abstract it into a single microservice, even though it's not just doing one responsibility, just because it's simpler. And hey, rather than sending SMS via a different microservice, I'm just going to send SMS or email via the same one. Like, that's fine to me. Because it's simple, it's the same concept. You don't have to go all the way of, hey, everything has to have its own thing. And so this would be like a completely separate, different application. Right? And as an example of that, what's an easy way of me showing that without? It should be fine as long as I don't grab production. Let's hope we don't. Is it going to? I'm not going to start it then. But anyway, so in our example, we have something called Send Engine, right, which sends out emails and other things as well. And this Send Engine has 3 components. It has a messaging interface, and this was terribly written. We are rewriting it. It also has a suppressor, which figures out whether or not we should suppress the email, i.e., if they opted out, or we've already sent one to them in the last day, or we sent one for a different program and we're doing multi-program suppression. So we sent one for X program, and so we don't want to send it for Y program, so we don't spam them. Basically, an anti-spam filter, right? And then the last one is like the dispatcher. And so these are like 3 separate applications, and they're connected via something called a queue. And so you have this kind of messaging queue, and so messages go in the queue, they get picked out by the suppressor, then they go back in the queue, then they get picked out by the dispatcher, as they kind of go in and out, in and out, in and out all the way. And this is actually quite common, this concept of a queue, or this concept of IPC, inter-process communication, or whatever that means. These kind of protocols to allow you to talk between these kind of distributed systems is very common, but they're so complicated. This is a very simple application. It probably consists of at least 1,500 to 2,000 lines, and we rewrote it in about 600. And we just went for more of a monolithic approach, and it was much better. And so the point is that sometimes with some of these things is that when you're kind of making these decisions, you'll see that certain companies will make decisions based on what they need. And so Google will have some applications that are very distributed. Everything has perfect design. Every component has its unique kind of purpose. You know, we sort of say single responsibility principle. Every class has responsibility. Every component has responsibility. But then you'll see some other applications where it'll be a bit more blurred. Because design is relative and it's always based upon what you need at that time. And so the one takeaway from this course shouldn't be, or every class I ever write has to have one responsibility. It should be, if I ever need to modify this, because in 10 days time, I'm going to have to add a new feature. In 100 days time, X person's going to have to add a new feature who's never seen the code base before. How easy is it for me to update the code? If you never need to update the code again, it can be the worst code in the world because you never need to update it. There's no need for good design if you don't need to change it. So we have these like one-off applications that we sometimes write for clients where we need like specific integration with their environments and we don't have the support in product. So we could spend 2 months writing the best well-designed application and spend like $400,000 writing something for a client where we may only get 15K per year. Or we could spend 5K with a really bad application that's only ever going to be used once and be okay. And so this is basically the decision that kind of is kind of left out of the course, is the fact that the decisions you make don't always have to be perfect. They just have to be relative to the changes you make. So mastering 2, sometimes there were some things I saw and I was like, okay, this isn't designed that well, but you're never going to change this. You're never going to update this, so sure. For example, the way your goals represent, if you don't use composite pattern, that's okay, because you're probably not going to be changing the way goals work in future milestones. You may have new goals, but you're not going to be changing the fundamental way they're structured, or you're not going to be adding like knots and stuff like that that are going to massively complicate everything. So if you're going to just like pass it from scratch every single time and not use composite pattern, that's fine, because you don't need to extend it in the future. But if you have this entity class, right, and this entity class has access to a controller, and it's doing all this wacky stuff to it, and it's like adding random entities, going and finding the player and randomly changing the player and moving X, Y, Z around, and you have 1,000 different functions in the controller that does all the spawning of entities. You know, you have a spawn spider function in your main controller. That's something that could change. What if I need 10 new spawners? I need a spawner for spiders, for mercenaries, for the 2 bosses. You know, these are things that you can expect to want to be updated because I want to spawn new enemies. And so those are the things that need the focus for the design. And so when we kind of look at this stuff, it pretty much comes down to the necessary need. And so to kind of wrap this all up and to kind of give you a final kind of context, I kind of want to show you 2 examples. And then also kind of briefly talk about like this kind of stuff. And so in procedural, right, you are very straightforward. You're a recipe book, you do X, you do Y, you do Z, you have a cake, right? It's basically just following a series of steps. There's no inherent structure to the way your data is organized. It's a mess, right? Very little people write procedural code these days, unless you're writing assembly. OOP is kind of pretty common, not necessarily the best way of doing it, but it's pretty easy. But the way OOP focuses on is it focuses on how entities interact with each other. The big mistake that people make is people think that OOP focuses on the entities. OOP does not give a damn about how your data is stored. All it cares about is how your entities talk to each other. That's it. That's legitimately the purpose of OOP, is how the entities communicate with each other, how they're aggregated with each other, and the relationship between them. It cares about the relationship between the objects, not the objects themselves. And so that's where single responsibility principle comes from. That's where the controller spawner comes from, is that relationship between the objects is clunky. you don't have a clean relationship. You don't have that clean abstraction of, hey, I need to add a new spawner. All I do is add the class. It already has the correct type. It already will work. I just have an interface to spawn it. I have all that logic in that single class. I don't have to add it to extra places. You have that clean separation between them. And then you have functional. Functional is all about the operations you're performing. It's all about trying to make it so everything is immutable in the best case scenario. Everything is composable. So you're generalizing on kind of the operations you're performing in some ways. It's kind of also focused on your data and the way it's stored, but it is very much focused on kind of how you're going to compose these kind of various different operations. Think of Java streams, right? Java streams is very functional. It's not really about functions. That's actually a big mistake. Like when people learn a functional language, for example, Haskell, right? One of the first thing they think is they go, oh, everything is a function, right? This is like the first thing that people think in Haskell. And the answer is actually not true. Everything's not a function in Haskell. How it actually works, technically, is more specifically, if you really want to break it down, in Haskell, everything is unevaluated. Everything is lazy. Everything doesn't have a value yet. So for example, in Haskell, the value 2, people think, oh, the value 2 is a function that takes no arguments and returns the value 2. And the answer is, well, kind of. But in reality, the value 2 is kind of like a partial function that has been fully qualified. So there's no more arguments to that function. There's no more stuff that has to be put into that. It's been fully qualified. All it's missing is when it's used. And as soon as you use something in Haskell or in a functional language, then it gets evaluated. So you can have infinite loops in Haskell. You can have infinite loops in your code. You can have an infinite linked list, and it won't break everything. Everything in machine learning is a function. That's true. Kind of, yeah. And to like tensors ruin my brain with that stuff. But oh, standard ML, not machine learning. Yes, you are correct. Yes, everything there is a function, especially when lambda calculus, right? When you get into that stuff. But like the misunderstanding is thinking that the reason why everything is lazy like 2 is that 2 is a function. But the reality is it's not really a function the same way like in math. Like you would have, for example, a function like, I don't know, x, which maps between like an int and it's a, I don't know, positive int, right? Like this is a function, but you wouldn't really like necessarily say the value 2 in math is a function, even though it can be expressed as in the same kind of way, right? You could express it as a function. Technically, it probably is a function because it has a domain, kind of. Yeah, it doesn't really matter. I'm not going to get into it. But at the end of the day, like, it's this distinction between what is... let's not get into it because I'm not going to, like, this is a 3-minute introduction to like functional languages. But the distinction here is that like functions in I guess the easiest way to explain it is a function in a functional language is not the same as a function in a non-functional language. And the distinction between what defines a function is really what it comes down to. And so, for example, your function in C doesn't really exist. It's basically just saying, oh, here's a block of code I want to execute. And it has a defined entry point and a defined exit point at which it will return to the previous function. Where in something like Haskell and stuff, you don't necessarily have the same definition because of things like partial application and stuff like that. But this is way above the scene. So let's skip that. Anyway. But like if you ever do learn Haskell, this is kind of, I guess, the initial presumption that people make. But this is kind of, yeah. It's funny. If you ever do the Haskell course, for the first assignment, if you think everything is a function, it makes the first assignment like significantly harder. But if you think everything is like a partial function, and view it that way, like it's in terms of like more of like a Haskell style function where it's like, hey, there's like arguments that's qualified to it. Anyway, it's like infinitely easier. And then data-driven design or data-oriented design is actually kind of what I meant here, but same difference. This is where you actually care about the format of your data. This is where you care about exactly how your data is structured, exactly what makes up your data. So this is where we get into things called SOA versus AOS, which is like how you're structuring your data. Are you structuring your data as a structure of arrays? So for example, like you have some kind of structure here, And then in it, you have a bunch of arrays. For example, you have, of course, it logs me out. There you go. And then you have saying, for example, yeah, cache locality. Well, cache locality is like a consequence of this. But yeah, you have the consequence of like, I don't know, like an integer array of positions. And then you would have like, I'm not going to do a string array. An integer array of velocities kind of makes sense to some degree as well. Though you probably like bind these two together because like typically if you're updating the position, you're updating based on the velocity. So you want the cache locality there to be high. It's fine though. And then maybe you have like another one for color, which is probably still going to be an int. Anyway, it's fine. And these are your colors. First, having an array where each object is a structure that has a position, that has a velocity, that has a color. Right? So it's kind of like flipping the representation of how the object is stored. And there's a bunch of other things to data-driven design or data-oriented design that's kind of fundamentally different to how you kind of treat OOP. But what you'll find is that regardless of what you do, you'll start to see these patterns will still pop up. You go off and you implement a very common kind of pattern, which is called ECS, right? And ECS is like a common game design thing. And basically you have like entities, for example, like a player. And the player would have like a movement component, right? Which is like, hey, this is a component that lets the player move. It also have these other components as well. And ECS is a little bit more than just this. ECS is also caring about like how the data is stored of these components and how you update these components, and it's caring about like the performance around that. And it focuses more on things like, for example, being able to run updates on GPUs and all this kind of craziness. So it's a little bit more than just like kind of storing a series of components. You have like a renderer component as well, right? But what you find is that it's basically just OOP, but with composition. So you have no inheritance. And so you still kind of get all these patterns. You still end up with things like strategy pattern. You still end up with, things like composite pattern. You still, effectively, the way a hierarchy is represented is composite pattern. You have like a player entity, and then within that player entity, maybe you have like their head. And then within the head, you have like a camera. Right? And then you also maybe have like a body or some legs, And then within the body, maybe you have like a collider that says, hey, when a bullet hits the body, the person takes damage. And so this kind of inherent relationship is composite, right? And so you get these consequences from this. You get these kind of representations of these structures. And so these are all questions that you could be asked in like an exam, not necessarily like ECS, but like this kind of pattern, for example, right? Recognizing this stuff. Builder pattern, all this stuff is very, very common. Pretty much builder pattern is used a lot in constructing kind of JSON documents sometimes. You want to construct very complicated JSON documents. It's very convenient to have like builder patterns to represent the layers of depth because it's kind of very simple to kind of represent that structure. If you're kind of generating it. Otherwise you use deserialization and serialization, which is probably easier, but still. I've kind of gone off brand even what I decided here, but anyway, so that's basically kind of those kind of points here. And what you'll find is that this stuff is pretty much like an entire career, and so you'll learn this stuff over time. And it's important to kind of in some ways understand these different methods, but you don't have to know all of them now, right? It's just kind of getting you. We'll walk into a code base and you'll see that they'll use functional, or you'll walk into a code base and you'll see that they will use data-driven design. As an example, for like a really good example, is in this kind of OLAP example that I showed before here, where we had all these kind of measures and stuff. Pretty much all visuals are rendered this way, right? Where we kind of go, okay, show me the completion method over maybe like I guess MPS. Like show me the MPS given for each state, and it shows you the MPS for each state. And then we grab all these results and we have like a trend chart, for example. That's actually executed on the GPU in some of our clients. That's like a data-driven design. Is like, how do you parallelize this algorithm? How do you store the data so that you can actually run like billions of records at once? We have these kind of different representations. I wrote like an algorithm that's that we're converting into like a paper actually, which like changes the way the actual data format's structured. So instead of being a cube, it's like a series of like fractals. So it's like a fractal cube that expands and it's stored differently, and it's very like funky and stuff like that. And it's able to process 1 billion records of data the same way as 1,000 records of data once you process it into that structure. And so it's actually non-scaling, which is really, really impressive. And so what you end up with is you never end up with one paradigm. No one goes, oh, this is just OOP. And so you kind of, one of the big things that you'll find is breaking out of that mindset and kind of being flexible of how you design things is very important. Anyway, let me kind of wrap this very big kind of abstracted talk up and kind of hopefully get to a point in the end. Don't worry about participation for this Tute. Everyone can get full marks for this because this is a bit of a high level, right? But in terms of like kind of what I would want you to take away from this is at least a form of appreciation of the fact that there's a lot that you won't know. And so the Dunning-Kruger effect is really real in interns. And it's basically this effect where the less someone knows, the more they think they know. And so when someone starts learning something, they basically think they know everything. And then over time, they think they know less and less and less. It's almost like kind of like knowing how much you don't know. So at the beginning, you don't know how much you don't know. So you feel like you know everything. But as you learn more and more and more, you realize that you know so little. And so you kind of have this understanding. And I mean, there's a very classical graph that's like, experience versus like your perception of knowledge. Right? And effectively, it currently looks something like this, kind of. Right? Not really like this. I guess it's kind of like that, and it kind of builds up over time, right? Probably a little bit less steeply than that, probably more like logarithmic. But anyway, it doesn't really matter. And so pretty much most people after they graduate 2511 is somewhere around here. And so when you kind of go and you do interns, soak all the information in, take all the perspectives, try to learn as much as you can, try to do internships, try to do stuff like that. And it will really advance your career. And definitely know your own value, set boundaries with companies. This is one thing people always do. The 3 tips I can give you for internships is don't ever, they'll maybe tell you how much you want from an internship, like how much money you want, remuneration. Never say the price. You never say the price first. Whoever says a number first loses in negotiations about money. So basically just don't say it. What things that you can say to kind of get around that is how much do you typically pay interns? What's your budget? What are you kind of looking for? Stuff like that. And you get them to say a number first, and then basically pretty much your intern, you have much control over that. But it'll be much more fair that way. Otherwise, there'll be discrepancies. The larger the company is, typically it's more standardized. A place like Google, I'm pretty sure it's like one price for everyone. But especially if your first job, don't do what I do, or don't do what I did, which is basically say I don't really care that much about money. I'm just here for the experience more than anything, because I was working at uni where I was like, uni's kind of paying for a lot of things. That's a really bad idea, because then you get underpaid and stuff like that. And I mean, it kind of worked out in the end, but still, you kind of want to value yourself because it's important principally, right? And the second thing is, once you do it, set boundaries. So like go offline. You don't have to, if you're working 9 a.m. to 5 p.m., you're working 9 a.m. to 5 p.m., right? At the end of the day, you're working at that company because you want the experience and you want the money. You're not working at that company because you want to work at 8 p.m. at night because someone asked you to do something, right? So you are able to say no to things. There's within reason, typically like an hour over, an hour to 2 hours of kind of overtime each week is in some ways expected. I work probably upwards of 60 hours, but that's because I'm salary based, not hour based, to be fair too. But even then, I have boundaries. So you need to set strict boundaries. If you can set them early, it's better. Expectations about things, a lot of people don't do that early on. And so, they're trying to balance a lot of things at once and it just doesn't really work. You need that kind of, I'm going to be online between these hours and I'm not going to be online after these hours. So if you message me at 3 p.m., I'm in a class, I'm not going to respond, right? And if you set those expectations ahead of time, the company can expect them and it's okay. I mean, if they really need you, right, they can ring your mobile phone, but like you're an intern, they shouldn't really need you. If they really need you, they should be paying you a whole lot more. And that's really what it kind of comes down to. So I recommend going for it, doing it. You'll have a bunch of fun if you do it. Apply for teaching. This is probably going to be my last term teaching, sadly, because I'm graduating this term, so I really don't have much reason to do it next year, and it's a lot of work to teach and to run courses and stuff. So I probably won't be course running or doing anything like that. So you guys are probably my last class ever. A bit sad. We can kind of reminisce next time. I know. I've been teaching for 3 years and like 8 months or something ridiculous. So it's a very weird vibe to realize that I probably won't be doing this next time. But yeah, anyway. It's 2:15 past. Let's just wrap this up before I blabber on much on. But yeah, so I think you all do pretty great. I've seen your experiences pretty well through the project, and we'll talk about this a bit more next time when we say goodbyes and stuff like that. But with design and all this kind of stuff like this is keep the concepts and keep learning. And I think the biggest thing is that like you don't have to be an expert in every field. And I think that's like one of the big mistakes is interns will come in and be like, I have no clue what this means, and just won't say anything. And they will just stay really, really quiet. And it legitimately is like the worst thing you can do, sadly, is staying quiet. You need to speak up and say, I don't know what this is. Can someone help me? Because if you stay quiet, it won't work. Like fundamentally, if you stay quiet, you'll just be behind. And in the long run, people will not understand. So you need to like, no one cares. Ask 1,000 questions, ask 1,000,000,000 questions. It's like, that's why people are there. You're an intern. No one expects you to complete it. No one literally, when I give tasks to interns and it's a task that I could do in maybe a day, I expect them to complete it within like 2 weeks. Like, I don't expect them to be necessarily good at the job. I expect them to want to learn and to actually try. That's all really anyone expects of you. And so pretty much that's it. Anyway, yeah, so there's a bunch of stuff here. For example, functional is something that I know very little about. Outside of doing it a little bit, I write a lot of functional code nowadays, more than I used to, but it's definitely something that I've got a lot less experience in, for example, as compared to something like data-driven design, which I have a lot of experience in, writing GPU code, stuff like that. And so I think that's one of the things that's really, really important is know your strengths and focus on it. Anyway, before I stop there, let's end the recordings, let's end the sharings, and I don't think there's a Tute this week. Anyway, that's not the right Tute. That's not the right Tute. There's just a lab 8, right? There's no lab 9. I'm pretty certain. Let's double check for the sake of my sanity. Yeah, there's no lab 9. So yeah, you guys get a relaxation. Hopefully lab 8 was really fine. And everything was good for lab 8, I'm hoping. Hopefully it was a little fun too, actually. I don't know. Like maybe you saw the impact of things. And with parallelism, you'll kind of see some performance stuff. We'll talk about that. And that's like the first time in this course I think we've really talked about performance, which I think is really kind of important when we're talking about design. So hopefully it'll be good. So we'll pop into each room. I'll go around marking. And we'll kind of spend some time with your groups and talk about things. And I think it's kind of quite critical that we have a meeting this week so we can make sure everyone's on the same track and I can kind of give you some recommendations on your design and all that vibe. We got one more week still, even though this kind of feels like I'm saying goodbye. I think just because the tone of the talk. Anyway, let us stop this recording. Yes, no, we're recording. And stop this recording as well.